Hello, in this video I want to take a look at three different integrals. They are three different rational function integrals, and they're three that are similar in the sense that you look at them and you think, huh, what do I do? But then they're all different. You have to do different steps in all three of them to get the answer. So, and it's not easy to see what to do necessarily for each of them. In the first one, we have this integral, a definite integral. We're going to have to evaluate it from 6 to 3 at the end. X divided by 3 times the square root of x squared minus 8. Now, you will probably see this problem as you're dealing with some inverse trig integrals. And looking at this looks a whole lot like an inverse sine or an inverse secant. But here's the thing. Inverse sine is 1 over the square root of a squared minus x squared. So that a being a constant, the number comes first and then the function. Okay, that is sine inverse. So it looks really close to secant. Well, inverse secant is 1 over u square root of u squared minus a squared. I suppose up here in the inverse sine, I could also say u squared, u standing for a function. This is my secant inverse. So that is right in that in our integral we have a function and then the number, so that matches up with secant. However, problems. I have this variable down low. I don't have that here. I just have an x up top. So it's not really looking like either of those. And now as I was thinking and trying to solve this problem myself for the first time, I thought, well, why not go ahead and try? Maybe it is secant somehow disguised. So I tried. I said, okay, well, what if u is the x? That means the du is dx. So I'm trying to force this integral to be a secant inverse. So I have to force everything to be two different squares. So I do this little guy. I've got my u squared, my a squared, but I still have this x up here, and nothing happened with my substitution to help me out there. So then I say, well, u equals x. So let's put in u equals x. I do a double substitution. I'm no closer. I cannot have a function up here if I want to do secant inverse. It has to be just a number up there. Okay, so we've got to back way up. It is not an inverse trig function. In fact, it is way easier than that. It is much easier. All we have to do is a u substitution and say u equals x squared minus 8. Du is equal to 2x dx. This is my u. There's my substitution. So du divided by 2 is equal to x dx. Let's make the substitution then. So this equals, I pull out the 1/3, and then I have this 1/2 for my substitution. So I have the integral from 3 to 6 of du over square root of u. Wow, this is actually not too bad. This becomes 1/6 times the integral of 3 to 6. I'm going to write u as negative 1/2 because this is just a power rule. Okay, so that 1 over square root of u becomes u to the negative 1/2. When I try out that integral, it's going to be add 1 to the exponent, so u to the 1/2. And then divide by that number. And we'll have to evaluate this from 3 to 6 after I plug back in for u. So if I divide by 1/2, well, that's the same as multiplying by 2, so I have a 2 up top there. And then I have the square root of u from 3 to 6. And now I have to plug back in my u, simplify the 2 6, so I have 1/3 times the square root of x squared minus 8, evaluated from 3 to 6. So by the second fundamental theorem of calculus, I have the square root of 36 minus 8 minus the square root of 9 minus 8. Evaluate at b minus evaluated at a. This gives me square root of 28 minus the square root of 1. And my final answer is 1/3 times the square root of 28 minus 1. Can't really simplify that anymore unless I choose to put it in decimal form. And if I do that, it gives me the solution of approximately 1.43. Okay, so that one turned out to be a fairly easy power rule once we recognized that. Okay, but what about this one? Now I have the integral of the natural log of x divided by x. Okay, so it's going to be u substitution of some sort. This is clearly not inverse trig. And also, I'm looking at this and I'm seeing natural log, and I'm also seeing an x down here. When I see that x down here, I'm envisioning 1 divided by x. See, that's important because I see the natural log and I see the 1 over x. So I'm thinking if u is equal to natural log x, the derivative is going to be 1 over x, and it's going to take care of that thing right there. But the problem is, and that gives me hesitation, is I don't have natural log of x, I have natural log of square root of x. So when I take the derivative of that, isn't that going to mess things up? Like I'm going to have a 1 over 2 square roots of x when I do the chain rule on it. Well, here's the thing. If you just sit there and stare at it and think and worry about that, you're not going to figure it out. Okay, it's easy to see that problem and just kind of get stuck, but you got to try. You got to go for it. And since our first instinct is to do u equal natural log of the square root of x, try it out. Okay, so then I have to take the derivative of it. Derivative of natural log is 1 over the inside function, so 1 over square root of x, times the derivative of the inside function. Well, what's the derivative of square root of x? That is 1 over 2 square roots of x. That's because x square root of x is x to the 1/2. So if I subtract 1, that's x to the negative 1/2. And then I also have that times 1/2. So look at this. This is really neat, actually. It's 1 over square root of x times 1 over 2 square roots of x. Well, square root of x times square root of x is just x. Oh, and I forgot my dx. So what do you know? I can substitute in, because I have 1 over square root of x there, and I should draw it in, a 1 over square root of x there. What do you know? And of course, this constant multiple of 2, I should multiply that over, so I have 2 times du over 1x times dx. Put in my substitutions, that 2 out front, 2 times the integral of u du. Okay, because I said this right here is my u, and then I said all of this is my du. All right, pretty neat. It just became the integral of u du, and that's a power rule, so it's 2 times u squared divided by 2 plus c, which is equal to u squared plus c, and since u is the natural log of the square root of x, it's going to be that squared. Now, do be careful. It's really tempting to put that square on the square root and say natural log of x, but that is not the case. This is the whole function natural log square root of x being squared, so we can't simplify that. We can't even bring that 2 down in front like the power property of logs. It has to stay just as is right there. All right, so another rational function that you try and take the integral of, and you think, what do we do? It's really tempting, again, to let u equal the denominator, but if I do that, the du of that is 50x. So I all of a sudden have an x to deal with. I don't have an x up there to substitute in for. So that is not it. This is where I hope you have your inverse trig functions memorized. Hope you recognize that the integral of 1 over a squared plus u squared du is equal to 1 over a times tangent inverse of u divided by a plus c. All right, so if you see a function where it's the sum of 2 squares down there, more importantly, the sum of where your variable is squared. So with that, while this still doesn't look exactly like our formula, we see it's really close. So let's try and force it to look a little bit more like that. How do we force it to be that way? Well, in the denominator, it has to be 2 squares. It has to be 2 perfect squares. 3 is not a perfect square. Well, yeah, but I can sure write it as the square root of 3 squared. Huh? Yeah, square root of 3 times square root of 3 is 3. So I can write it that way. 25x squared is the same as 5x squared dx. So what that means is I now have a equal to the square root of 3, u equal to 5x, and I'm letting a equal that so that when I do these substitutions, it is going to look exactly like the formula. Now I do still have to worry about this u substitution and do du, and that gives me 5 dx, which means du divided by 5 equals dx. And when I put in all my substitutions, I have a 1/5 out front times the integral of 1 over a squared plus u squared du. What do you know? That looks exactly like my tan inverse formula. So let's just plug it all in, and we get 1/5 times 1 over a times tangent inverse of the u, which is 5x, over the a, which is square root of 3, plus c. So let's just write that one more time when we combine the numbers out front. And this is my tan inverse. So in this video, we've seen 3 tricky rational functions that all look kind of similar. They all give you pause and be like, what do I do to solve this? How do I start? And they all look similar a little bit, but they all have vastly different outcomes and answers.